Okay, so we talked in the last couple of lectures, lecture 3 about bauxite, lecture 4 about how evaporite halite deposits form, how magmatic sulfide deposits form within a magma chamber beneath a volcano, and how volcanogenic massive sulfide deposits form at mid-ocean ridge spreading centers. We're going to transition now in lecture 5 to talking about how do you find an ore deposit. Imagine that you graduated and someone hired you, presented you with a map of the world like this one, and asked you to figure out where they would go look for a new evaporite halite deposit, or a new magmatic sulfide deposit, or new bauxite deposit. What clues would you look for? How would you take this really large-scale map of the Earth and hone in on really small areas of Earth's surface to figure out whether or not there might be an ore deposit located beneath the surface in that particular area? So I'm going to build this out over 2 lectures and introduce you today to the impacts that chemical and physical weathering have on ore deposits beneath the surface, so you can get a sense of what the surface signals are and the subsurface signals are that geologists use to explore for new ore deposits buried beneath the surface. Now, one of the things I want to make sure and highlight up front, because I showed this slide in one of the previous lectures, you're looking here at essentially a histogram, where if you look at the top, you can see that each of these rows is a unique type of ore deposit. And I don't need you to memorize the data on this slide. We've got a variety of different ore deposit types important for a variety of different natural resources. Resources like lead and zinc, uranium for nuclear power, gold for technology and currency. We've got copper deposits that we talked about in Bingham Canyon in Utah. And you can see that the x-axis at the top is age in billions of years, where here we have 3 billion years ago, 2 billion years ago, 1 billion years ago, and then the present time. And what's really important to understand as we start talking about exploration for ore deposits is that ore deposits are finite. And that means that when we look at any one particular type of ore deposit, you can see here as a function of time, if we go back older than 2 million years ago, there are no aluminum laterite bauxite deposits on Earth. None. And that's because they form at the Earth's surface in hot, tropical, wet environments. And as a result, they are weathered and eroded rapidly on geologic timescales. So if I build this out, we can see here between 2 billion and 1 billion years, there also are no bauxite deposits that are left on the surface of the Earth. All of the deposits that we currently mine for aluminum in the bauxite resource form here within the last few tens of millions of years. And so what's important when we think about mineral exploration is that for each of these different types of ore deposits, nature makes them at a rate that is much slower than the rate humans are currently mining that resource and using it, which means that these resources are truly finite. So as we continue to explore for new resources, it's also critical that we continue to engineer new ways to recycle all of the resources currently embedded in the products consumed by society. I showed this slide in lecture 1. Here you see the 7 metals of antiquity: gold, which we've been using since about 6000 BCE, copper, silver, tin, lead, iron, and mercury. And each of these resources put places on the map in the ancient world. So if we look here at a map of Anatolia, or modern-day Turkey, Mesopotamia, and Arabia, going back thousands of years, each of these areas was literally put on the map because of the resources that humans tripped over at the surface. So here we have tin and copper. Here we have silver and copper. Here again we have silver and copper. Here we have copper and tin. And it's important that you think about what it would have been like for humans to explore in this area thousands of years ago. We didn't have any of the modern tools that I'll talk about today and in lecture 6. So when humans found resources, they literally had to find the resources at the surface. So here's a map of England that I also showed a few lectures ago. Here's Great Orme, and this was an area where humans, at the dawn of the Copper Age, thousands of years ago, they found copper at the surface. And when they found that copper at the surface, it was sometimes metallic and shiny, as you see here in this photograph. But it was often discolored, as you see in the image here on the top right and the two lower images, where that copper, when it's exposed on the surface of the earth, the copper metal, reacts with rainwater, regular rainwater that is slightly acidic, something I'll come back to today, and it produces this really nice green patina that's very characteristic for copper. So in the image on the top left, each of these holes is a tunnel where humans observed the presence of this copper-rich patina at the surface, and then they dug miles of tunnels into the rock to extract copper and used that copper, and that's what transitioned us from the Stone Age to the Copper Age. You've seen this image before. This is the Bingham Canyon mine just south of Salt Lake City in Utah in the western United States. And this is a photograph taken from the space station. So in the next few lectures, I'll zoom in and you'll get to see the actual scale of this deposit. It measures several miles across and almost a mile deep. And I asked a question in a previous lecture, why does this hole exist? If we go to western United States, here's Utah, a map on the top left side. And then if we zoom in on Utah, and this small black box here represents the greater Salt Lake area. Here's Salt Lake City proper, and here we have the Bingham Canyon pit. And what put this particular spot on the map was the fact that, as you can see in the photograph on the lower right, which you've seen before, the rock at this particular place, south of Salt Lake City in Utah, is anomalously enriched in minerals that are anomalously enriched in copper. So the value of this rock at modern prices is significantly higher than the value of all similar types of rock around the world, which allows a mining company to extract the rock, process that rock, purify the copper, and sell that copper to make a profit. And that's why that hole exists. If that rock were normal granitic rock, as you might think of in a kitchen countertop, then no mining company would spend any money mining that rock. So here is an image to give you a sense of that scale of the Bingham Canyon pit. So approximately 4,000 meters in diameter and over 1,200 meters deep. And the Bingham Canyon mine, which has been operating since about 1906, has produced over that time, so let me make sure I say this correctly, from 1906 to 2020, the Bingham Canyon mine has produced 22 million tons of copper, which is equal to the amount of copper that humans currently consume about every year and a half, which, if you think about the amount of copper our global society consumes, it means that we have to continue to explore for new ore deposits, such as Bingham Canyon, that are enriched in copper, and we have to make sure that we recycle all of the copper currently embedded in the products that we consume. Because if we think about, for example, providing electricity to the more than 1 billion people around the world in less developed countries who currently do not have access to electricity, this is the type of ore deposit that must be found and mined in order to provide the copper to build that electricity infrastructure, which we know is critical for the developing world for a variety of factors. For those of you interested in history, there are 3 numbers on the top of the slide. The state of Utah is here in red, and I would encourage you to look into the history of the Bingham Canyon deposit. Bingham Canyon is named after 2 brothers who had the last name Bingham, who were among the early Mormon pioneers who fled Missouri and moved west by foot, by horse and carriage. And in the late 1880s, 1890s, they found Bingham Canyon, but at that time they couldn't mine it for reasons I'll go into. But again, I would encourage you to look at the history here. The state of Colorado became a state in 1876. The state of Nevada was absorbed into the Union in 1864 during the Civil War. And the reasons that Colorado and Nevada were absorbed into the Union before Utah is that in Colorado and Nevada, there were ore deposits at the surface much richer in copper and gold and silver than Bingham Canyon. And so Bingham Canyon was not absorbed by the Union because there was an interest in Washington, D.C., in essence of persecuting Mormons and not allowing them to become part of the United States. And just like I showed you in a previous lecture for the population of California after the 1848 gold rush, here we have population on the y-axis versus time from 1850 through 2013. And I just want to give you a sense of the immigrant population that moved into the Salt Lake City area. You can see in 1850 it was effectively zero. And notice that population continued to increase. And in 1906, when the mining company first started digging the open pit that we now call the Bingham Canyon mine, you can see that the population continually increased. And today, this one mine, Bingham Canyon, contributes about $1.5 billion annually to the economy of the state of Utah. So this was that image I showed a few lectures ago, where we had the California Gold Rush in 1848, 1849. And you've already been tested on this on exam 1, so I won't ask you questions about this on exam 2. But remember when I talked about the California Gold Rush, what was really a stampede of immigrants from around the world, mostly from Europe and the eastern United States to California, we saw a similar impact, right? We saw a complete change in the demographics of that particular area after gold was discovered. Now, importantly, remember that the gold that was discovered in California was really easy to find. And I have a little animation here that shows you people literally tripped over that gold. You could see it with the naked eye. It was at the surface. It was low-hanging fruit. And this has been the story for thousands of years. So if you look at each of the 4 photographs here, on the top left is a photograph where all of the shiny mineral here is galena, which we mine for the element lead. All of this brownish shiny material here in the center is sphalerite, which we mine for the metal zinc. All of this very shiny goldish colored mineral here is the mineral pyrite, which we mine both for iron and also for sulfur. And then on the lower left, this little veinlet of shiny mineral here that runs bottom right to top left is the mineral chalcopyrite, which we mine mostly for copper, but we also extract the iron and sulfur, and we can sell those for a profit. And when I say we, I mean the mining industry. So for thousands of years, if we go back to the metals of antiquity that we can read about in the Old Testament, humans literally tripped over ore deposits. They would observe at the surface rocks like you see in all 4 of these photographs, and they were low-hanging fruit. There was very little exploration strategy except for walk around over a large enough area and find metallic minerals that we can extract. The case today is completely different. So today when we think about finding ore deposits, imagine that this is the ground surface in black, and we're standing on the surface of the earth. And we have ore deposits that are buried under what we call cover. And I want you to think of cover as soil or dirt or sediment, the same type of soil or dirt or sediment that you might have in your backyard or at a local park. And so now what we have is we have exhausted most of the mineral deposits that intersect the Earth's surface, meaning those that you would literally trip over. So geologists now are required to figure out ways to find ore deposits that are buried tens to hundreds to, in some cases, thousands of meters below the surface. And the question is, how can you actually do that, right? If you're at the surface and you look down at the Earth, what's beneath the surface is effectively opaque. You can't see beneath the surface with the human eye. So we need a variety of tools that let us see below the surface. One of the things that's important that allows us to infer the presence of an ore deposit below the surface is the result of chemical and physical weathering. And I want to give you just a snapshot of how chemical and physical weathering change the color of ore minerals in rocks that are close to the surface and in some cases might intersect the surface, and how chemical and physical weathering can actually disaggregate and dissolve ore minerals and then move the metals contained in those minerals around so that we can measure them in soils and use those measured concentrations to prospect or explore for ore deposits. So each of you listening has probably seen a roof that looks like this, where the roof was originally copper metal and it would have been a beautiful shiny color. And as a function of time, rainwater and snow and sleet, moisture from the atmosphere, chemically weather that copper and react with the copper metal to produce this beautiful green patina. So if you look at any roof that's now covered with this beautiful green patina copper, when it was first built, it would have had a very shiny copper roof such as the one on the right-hand side. So we know as geologists that this chemistry is happening. It's happening not only on roofs, but it's happening in any rock that contains minerals which are enriched in copper. You can think of the same thing happening to the Statue of Liberty. So if you were to go back to 1886 and you were to look at the Statue of Liberty being erected in New York Harbor, the entire statue would have been this beautiful shiny copper color. And over the last 140 years, that copper has reacted with moisture in the atmosphere, rainwater that falls on the copper, and now the entire surface is this beautiful green patina. So what that means for a geologist is that if you observe rocks on the surface that have this beautiful green patina, just like humans did in ancient England at Great Orme, it's a clue that there might be a mineral deposit below the surface that's enriched in copper. So how does that happen? Well, imagine that we've got copper, and that copper exists on the surface of the earth. Oops, trying to play the video here, I forget how we do that. Oh, there we go. So imagine we have copper that exists at the surface of the earth, and rainwater and moisture in the atmosphere fall on that copper on geologic timescales, right? We can see this happening to copper roofs in human timescales, but imagine it's happening on geologic timescales, thousands to tens of thousands, hundreds of thousands, millions of years. What happens to that copper as a function of time is that it ages. So as that rainwater and atmospheric moisture continue to chemically weather copper at the surface and also beneath the surface, you can see here, as a function of time, that beautifully shiny copper metal, after a period of only 25 to 30 years in the panel on the lower right, has been completely transformed so that it has now an entirely new color. And this is a result of what we refer to as chemically weathering, natural aging, as copper metal reacts with atmospheric moisture. Here is a photograph from the Caribbean, an island that I'll come back to in a few minutes with a map. And all I want you to see here is now we've got a human, and you can see that he's staring at this green rock here and these green rocks over here. And if you look at this whole hillside, you can see that these are the only two places where this beautiful green patina exists. And what geologists know is that that green patina is a hallmark for the presence of copper in minerals below the surface. So this is something a geologist would look for and then use as evidence to do a more thorough investigation of the potential for a copper ore deposit in this area. So now let's talk about weathering and metal transport. So again, imagine you're on the surface of the earth up here, and we've got a rock that's beneath the surface. And within that rock beneath the surface, we've got minerals that contain copper, minerals that contain lead, minerals that contain zinc. As rainwater hits the surface of the earth and percolates down into the subsurface, on geologic timescales, that rainwater will react with and dissolve some of these minerals, not all of them, but it will dissolve some of these minerals during chemical reactions, during weathering, and it will advect or transport some of those metals away from the central parts of the system. So now we've got an example here where imagine rainwater, which has a pH of about 5.7. Rainwater is not neutral. It has a slightly acidic pH because of the dissolved gases in Earth's atmosphere. What happens is that rainwater percolates through a mineral deposit. Well, as I said, it's going to chemically react with all of the minerals in this rock, and it will leach some of the metals and move them away from the ore body. And in some cases, it can move them away from the ore body and actually return them to the surface if that water becomes part of the groundwater system that intersects streams. So what is chemical weathering? I'm going to play a video now, and I'm going to let you watch it first, and then I'm going to walk back through it with you. So two beakers. The beaker on the left is water. The beaker on the right is acid rain vinegar. And you'll see a hand that's going to drop minerals in each of the two beakers. And I want you to watch what happens to the minerals after they're dropped into the two beakers. Remember, the beaker on the left is pure water. The beaker on the right contains water plus vinegar and has the pH of acid rain, so it's slightly acidic. Notice what happens. The mineral on the left is effectively not in any way interacting with the water, whereas the mineral, when we dropped it into the beaker on the right that contains acidic water, notice that that acid water reacts with the mineral everywhere along its surface and disaggregates the mineral, or meaning breaks up the mineral, and notice that that mineral then is moved away from where it was at the beginning of the video. Right? So if we go back and we see here that the mineral on the right is dropped into the lower right side of that beaker, notice immediately you can see this little plume of material that's rising. And as I just play this through manually, look at the surface. Right? Look at the surface of this mineral. You can see that the acid rain is chemically weathering that mineral surface, disaggregating the mineral. And now all of that mineral that's part of the water over here can move with the water if the water were, for example, moving in a stream, or the water, for example, were moving as part of groundwater beneath the surface. Here's another example of chemical weathering where we have nails put into 5 different plastic bottles. One simply has air on the left. One has a drying agent with no liquid. The one in the center is water plus air. The one second from the right is salt water plus air. And the one furthest on the right is water only. And I want you to see what happens to each of the nails. All of the nails are the same nails. So watch what happens as a function of time. Right? Nothing's happening when the nail is in contact with air or the drying agent. And now we're zooming in and we're looking at the nail that is in salt water. And for salt water, think of the same type of water you might use to make pasta, just dissolving halite into that water to create salty water. Here we have the nail that is in water plus air. And notice already in the span of only minutes, focus in on this part of the nail, and what do you see happening? You see a color change. Nothing happening in the air only, nothing happening to the nail in the drying agent. And if I zoom over here to the nail in salt water, you can see that it starts to become discolored, as does the nail in the water plus air. And remember, water that's in equilibrium with air, rainwater, is slightly acidic. So here we have a second example where we have a steel nail, and a steel nail is mostly iron, so it's mostly consisting of the metal iron. And what we see happening is the iron in the steel nail is being chemically attacked or weathered by the salt water and the slightly acidic water over here. So this is another example where if we were to think about this in nature, imagine rocks that contain minerals, and the minerals contain the metal iron. As those minerals come into contact with rainwater that is slightly acidic, or ocean water perhaps, then those minerals with iron will be chemically weathered, and that iron can become mobile, and now it can move as part of that water system. And this is exactly what we see in lots of different types of ore deposits. So lots of ore deposits have the mineral pyrite. And pyrite I show here on the lower left. It has the mineral formula iron and 2 sulfurs, iron sulfide. And all I want you to take away from this reaction, you don't have to memorize it for the exam, is when pyrite reacts with rainwater, and that rainwater is slightly acidic and also contains some dissolved oxygen inside the rainwater, the oxygen in the water chemically reacts with pyrite and weathers it to produce an entirely new mineral that we refer to as limonite, which is shown down here on the lower right photograph. And that limonite, when it's produced, also releases hydrogen ions, which make the water acidic. That reaction also produces sulfate ions, which makes the water acidic. And this is what leads to what we commonly refer to as acid bind drainage, something I'll come back to in a future lecture. So just to recap, if we have rocks just beneath the surface or rocks that intersect the surface, and meteoric or rainwater falls on the surface and contains dissolved oxygen and is slightly acidic, it will chemically weather pyrite and produce what we commonly call rust, but what is the mineral limonite, which again, to a geologist, if we were to see limonite at the surface, that's an indication or a clue that there might be minerals such as pyrite or other minerals enriched in iron below the surface. So here's a slide to give you a sense of what I mean by advection or transport. Now I first want to focus your eyes on the image in the lower right. So you can see the trees here represent the Earth's surface. And all I want you to see is that below the surface there is an ore deposit or an ore body that has a roughly vertical shape, right? It sort of looks like a finger beneath the surface. And on its left and its right side are rocks that contain no ore minerals, nothing that any mining company would extract. In this particular case, the ore body is enriched in the minerals galena, which is shown lower left, which is a lead sulfide, and it's enriched in the mineral sphalerite, upper left, which is a zinc sulfide, and zinc and lead are both mined from ore deposits that contain sphalerite and galena. Now notice here on the image on the top right, the y-axis is metal concentration in the soils at the surface. Okay, so imagine we now collect samples of soil from the entire surface here, and we measure the abundance of lead and the abundance of zinc. What you can see is that the greatest abundance corresponds spatially to where the ore body is located. And that's because the soil that evolves right here is effectively soil that is produced by chemical weathering of the zinc and lead-rich ore body. Now, as meteoric or rainwater falls on the surface and chemically weathers the sphalerite and the galena, what you can see in the concentration plot on the top is that some of the zinc is dissolved and it is advected or transported away from the ore body on both sides. And you can see that some of the lead, less lead, but still some of the lead, is also dissolved and advected away. So one of the things that is commonly done to discover ore deposits is soil samples, where you can collect soil samples over a very large area and measure the abundances of, in this case, zinc and lead, and you look for what we call alteration halos. And I'll show you a slide in a few minutes to make this point more clearly. But the key here is that zinc and lead are being dissolved from minerals in the ore body, because of chemical weathering of the ore body by rainwater. And that then makes zinc and lead soluble in the water, and they essentially move as part of the water that is the groundwater system beneath the surface. So you can look at an image here of mountains. In this particular case, we're looking at mountains in Alaska. And all I want you to see is that the mountains would be high elevation, and here in the valley we have low elevation. That's all I want you to see right now. High elevation, low elevation, and water flows downhill. Now imagine in the mountains at high elevation, there's an ore deposit that contains minerals that are enriched in copper. And on geologic timescales, rainwater, sleet, and snow fall on that ore deposit high up in the mountains. That rainwater chemically reacts with the copper-rich minerals in the ore deposit and then washes some of that copper down to low elevations as part of the streams that are draining the mountains. What could you do in this area to find if there is a copper-rich ore deposit in the mountains? Right? It's like looking for the needle in the haystack or trying to hit a bullseye on a dartboard. Well, if we zoom in to this particular area in the Dominican Republic, I'm going to show you how a mining company actually did this. So here we have the Caribbean Sea. Here's Florida here, top left. Here's Miami, the Florida Keys. Here's Cuba. And I'm going to zoom in now on the Dominican Republic, which I've outlined in red. And this is what the Dominican Republic looks like from the air. It's a heavily forested country. And so from the air, you can see on the left-hand side, we've got a river. And you can actually see on the right-hand side of the photograph, this is an operating ore deposit. And I want to give you a sense of how this ore deposit was discovered. The ore deposit there is known as the Pueblo Viejo mine, and it's an ore deposit that's been operating for several decades. And this is what it looks like from a helicopter. And the way that that ore deposit was found was by collecting samples of sediment or soil or dirt from streams at the ocean here on the right-hand side, and then progressively uphill. So you're looking now at the surface in this part of the diagram, where all of the blue are rivers or streams, and then this would be the side profile. Each of the symbols is an area where a geologist collected a sample of soil or a sample of sediment from the bottom of the stream. So imagine that you're a geologist here on the right side of the diagram, and you start walking upstream. You collect a sample here. You continue walking upstream, you collect a sample here. You continue walking and collect a sample here. And you continue to sample, and each one of these samples you send back to the lab, and they analyze the sample to measure the concentration of copper. The different symbols here are an indication of the relative amount of copper in the sample that you collected. So in yellow, the concentration of copper is the average crustal concentration. The triangles are samples where the concentration of copper is slightly elevated, and the stars here on the bottom side of the diagram and the top side, the stars are where samples are anomalously enriched in copper. And in this case, the geologists were able to determine that slightly upstream from these soil samples and stream sediment samples enriched in copper, there actually are copper-rich ore bodies directly below the surface. So if you travel to Pueblo Viejo, or the region in the Dominican Republic where Pueblo Viejo is located, this is a sense of what you might do. Here's a stream on the left-hand side, and you might put on your boots and you would walk either along the edge of the stream or in some cases maybe in the center of the stream, and you would use, in this case, a really fancy sampling device called a kitchen spoon, and you would sample the sediment and soil, put it into a bag, and send it to the lab and have them analyze it for copper or gold or silver. And then you would get a map that looks like this. So on this map, if we look bottom left, Here we have the Dominican Republic, which shares the same island with Haiti. And all I want you to focus on are two streams. On the right-hand side, this is the stream called Arroyo Claro, okay, which starts here at low elevation, and then you can move to higher elevation towards the top of the map. And the second stream is Arroyo Colorado. And again, notice that at the bottom of the map, you're walking uphill towards the top of the map. Each of the dots represents the physical location where a geologist stood and said, I'm going to take a sample here, I'm going to take a sample here, I'm going to take a sample here. They send those samples to the lab, and then the size of each dot is an indication of how much copper is in that particular stream sediment or soil. So the larger dots here contain more than 500 parts per million copper, and the smaller dots here contain less than 100 parts per million copper. Notice that for Arroyo Claro, not a single one of the samples yielded copper that contained more than 100 parts per million. So if you were a geologist working in this area, right away you would know that Arroyo Claro is not a place you're going to return to. But Arroyo Colorado, as you move progressively upstream to higher elevation in the mountains, the concentration of copper gets higher and higher and higher and higher. And in fact, these two small ore bodies right here are what a mining company is now mining for the metal copper. This is an example in the Pueblo Viejo area where indigenous communities, going back hundreds, if not thousands of years, had also used what you might think of as prehistoric mining techniques. And this is a mine shaft that was built several hundred years ago to extract copper in this area. This is a slide that shows one of my most recent PhD students, Nikita La Cruz, who graduated with her PhD from the University of Michigan last year in 2019. Nikita is from this little dot here in northwestern Guyana in northern South America. And Nikita's PhD focused on stream sediment sampling throughout the country Guyana, which is about 85% densely forested. And this is Nikita in a stream, and she is sampling sediment from the bottom of the stream. So this is something that geologists do right now around the world as they explore for new ore deposits to satisfy society's consumption. Okay. So that's a bit on weathering of ore deposits that intersect the Earth's surface. We've got color changes owing to chemical weathering, where rainwater will chemically react with minerals in the subsurface. We've got dispersion or advection or transport, all synonyms for the movement of metals as a result of chemical weathering. So that leads to a question. What if you had no visible evidence at the surface, and you had no strong evidence by way of soil samples for the presence of an ore deposit? How would you actually detect a mineral deposit if there's nothing on the surface, such as the green patina for copper? What would you do? Before we get there, I want to give you a sense of why this question is so important. So I want you to look at the diagram here. And imagine that you and me are standing up here on the surface of the Earth. The y-axis on the left-hand side of the diagram is the depth of cover, meaning the depth below the surface of the Earth in meters. So 0 to 1,000 meters, or 0 to a kilogram, or about half a mile. The x-axis here are years. And each of these years correspond to the year that a particular type of ore deposit was found around the world. So when you look at this diagram, all of the yellow dots are gold ore deposits. All of the green dots are base metal ore deposits. Think of iron or copper. All of the open dots, as you'll see when I allow as you'll see when I scroll through the slides, are uranium, and then all other types of ore deposits. Now, what I want you to see right here is if we go back to the time period 1900 to 1920, all of the ore deposits that humans found had to exist at the surface of the Earth. right? So we were still dealing with ore deposits that we tripped over. Notice what happens as a function of time. From 1920 to 1940, notice that on average, as shown here by the pink area, we start discovering deposits deeper. Okay? By 1960, we're starting to see more deposits, in this case base metals, being discovered deeper. We're still discovering deposits at or near the surface. But as a function of time, since 1960, notice the trend is that ore deposits are being discovered at deeper levels of the Earth's crust. Now, there's ultimately a finite depth to which you can mine an ore deposit, and that's based on the price of a metal, something we'll come back to in a future lecture. But what I want you to see when you look at this particular slide, and you think, what does this mean? Why do I care? What it means is that increasingly, year over year, as we continue to explore for more ore deposits at the surface of the Earth, we're finding fewer of them. And that's because we're finding all the ones that are at the surface that can be found. It means that moving forward, 2020 to 2030, 2030 to 2040, mining companies are using a variety of other high-tech tools, not just looking for the green patina on the surface, not just looking at stream sediment samples where they can measure the abundance of copper or gold or uranium, but they're using a variety of tools that for now you can think of as akin to X-ray vision, tools that allow us to use technology to look into the subsurface and actually map the subsurface without having to dig a hole. And that is the future of mineral exploration and what we'll talk about next.